Welcome to an ECE 501B review session for exam number 2. I hope I don't need to remind you the next time that we see each other, unless it's in office hours, once we are in this room, Wednesday, the 11th of November, is exam number 2. Right? And it will be not at this time, but it will be at the normal class time, which is 4 o'clock. The process, we've gone over this in class, but the process is this time you get 3 sheets of notes, front and back of each sheet. You can have a calculator and something to write with, and then everything else is a no. No textbooks, no course notes, no cell phones, no neighbor, no computers, etc. Okay? Process should be consistent with what we've done in the last exam. In terms of topics, it's Chapter 5 material and Chapter 6 material. It's all of Chapter 5. The first exam actually covered some of Chapter 5, down to, I think, page 79, if you've got the textbook memorized. But this is all of Chapter 5 and all of Chapter 6. Chapter 5 deals with eigenvalues and eigenvectors. Chapter 6 now gives us another layer of where we can play. We were on vector spaces. Now we're going to add on to those vector spaces an inner product. And the combination of a vector space with an inner product now gives us this inner product space. Now, because the content is cumulative, meaning you have to know chapter 1, 2, 3, 4 to really make sense of 5 and 6, we will focus on the material in terms of creating the questions, but we may have to rely on, obviously, vector space concepts, being able to manipulate, knowing about a linear map, etc. Some of those earlier ideas have to be used in order to address Chapter 5 and Chapter 6 material. Had a little bit of a pause. But the material will be homeworks 5, 6, and 7. The homework that you have turned in prior to this exam is fair game, starting with Chapter 5. Chapter 5, 6, and 7. And what you want to do is, if you have Chapter 5 and 6 memorized, what you want to do, in addition to having it memorized, is know how to apply it. So what do those theorems, those propositions provide you with? Now, how do you actually apply that with a problem statement or something that I might ask you to build or create? So let's sort of go over the material that is maybe more critical. I mean, I basically made a list of all the corollaries, the propositions, the theorems in the 2 chapters. But now I tried to identify some of the more critical theorems and propositions, and I'll walk through those. That doesn't mean that the others are off limits, but these are sort of the ones that I can sort of see contain the majority of the material, or the substance, the main substance in chapters 5 and 6. For example, Theorem 5.6. That basically says that if the lambdas or the eigenvalues are distinct, then the eigenvectors are linearly independent. And again, I'm sort of paraphrasing these or doing this in very quick fashion, but you can go back and study these particular theorems, propositions, etc. But that's a pretty key result. If you now have distinct eigenvalues, then you know something about those eigenvectors, and the something that you know is they're linearly independent. And now if you have enough of those, you might be able to span a given space. You may have to complete the space. But how many eigenvalues can you have, potentially? The dimension of the vector space V, which typically we say is little n, Nevada. And those eigenvalues may not be distinct. You might have repeated. But you do know if they're distinct that those eigenvectors are linearly independent. You don't know whether or not the repeated ones provide linearly independent eigenvectors. We may have to create generalized eigenvectors later on. We haven't done that yet in this class. But we know that the most we can have is the dimension of V in terms of eigenvalues. And that's another theorem, or corollary. That's corollary 5.9. But theorem 10 in chapter 5 says that every operator on a finite dimensional complex vector space has an eigenvalue. So this is basically the existence of eigenvalues. And this is on a complex inner product space. When we have real inner product spaces, this goes out the window, meaning you could have an example that does not satisfy the conditions stated in Theorem 10 of Chapter 5 if I gave you A equal to 0, 1, minus 1, 0. That's not going to have any real eigenvalues. So that matrix, if this was, if we were playing, if now V is R2, then A has no eigenvalues. And I could give you a linear map. You could give me the linear map that does not have any real eigenvalues just based on that matrix representation of the linear map. That's the processing that I want you to be able to do. We could have changed these diagonal entries to pretty much be whatever we wanted. And I hope by the end of the course, this actually, the lambdas of A are at minus 3 plus and minus J1. They're not real. And this is sort of a standard structure for representing complex eigenvalues with real numbers. And we might have block diagonal or block triangular matrices later on in the class. But now this would be an illustration of showing or illustrating why, if you have a real vector space, oh, why did I say CIPS? I don't think I need the I, do I? I just need a complex vector space. I'm so back in, or I'm back to the future, I guess. I was into the future, wasn't I? So this should have been just a complex vector space. It's not a college vector space, it's a complex vector space. I see that CVS. We were at 7-Eleven earlier, now we're at CVS. Go figure. So one of these theorems will be a Walgreen theorem. Okay, somewhere. We'll have to pull that out. When I used to teach this class in its earlier version, I don't know where I'm going with this, but we were talking about matrices. And we had, I don't know, I think I was talking about some inversions. And I had U, no, I think I had V and W, and then that was equal to the identity element, or identity matrix. I was talking about matrix inverses. Going home that same night, I pull up behind a VW and an element. And I go, oh, this can't be chance. That didn't make any sense, did it? But anyway, I had a VW equal an identity element. Only me, right? All right, let's get back to this. So, where were we? We were on Theorem 10 in Chapter 5. Theorem, or Proposition 512, tells you about the different invariant subspaces of an upper triangular matrix. And so you should be comfortable with the matrix representation associated with an upper triangular matrix and what that means for invariant subspaces, and how those basically sort of build on themselves. So here we have an invariant subspace relationship of upper triangular matrices. Meaning if we now had, let's say, -3, 1, -2, 0, 0. Well, I don't want to put so many zeros in there. Let's say this is a 4 and a -5. That's an invariant subspace, isn't it, of that operator or that matrix. 1, 0, 0. Then if we looked at the next one, maybe if we viewed this as like x, y, z, the first coordinate being x, the second coordinate y, the third coordinate z, then the xy plane is covered by the first two columns of that matrix A. And that's an invariant subspace. If you're living in xy and you operate on it with this upper triangular matrix, you're going to stay in that xy plane. You're going to stay on the floor. But if you now have an xyz, now you're going to be living in the three-dimensional space. Again, these subspaces sort of stack up on themselves. If you are on the x-axis, you'll stay on the x-axis if you operate on it by this upper triangular matrix. If you start in the plane, you'll stay in the plane. If you start in the three-dimensional space, you may stay there, but you're not guaranteed of moving to any particular lower dimensional space. Is that okay? So that's the relationship between these invariant subspaces of upper triangular matrices, and I want you to have a grasp of that or a feel for that. The other thing is, when do you have upper triangular matrix? And that's Theorem 513. Anytime V is a complex vector space, then, and T is a linear operator, you're guaranteed that there is a basis that will put that into a matrix representation that's upper triangular. So if somebody now says, oh, you have a complex vector space, boom, now you have a lot of things possible. If they now tell you to show something, you can at least say, well, let's, without loss of generality, assume that the matrix representation is upper triangular by Theorem 513, and then you can move on. You can say, okay, now I have this upper triangular representation. Now I know something about invariant subspaces, etc. What else do we know relative to Chapter 5, which is dealing with eigenvalues and eigenvectors? If we have an upper triangular matrix and all of those elements on the diagonal are non-zero, What can you say now about that operator? Now it's invertible, isn't it? So this is now an invertible operator, which might be important. Now that we're playing with upper triangular matrices, those diagonal entries are precisely the eigenvalues, aren't they? Those are the eigenvalues. So now if somebody gives you an upper triangular matrix and they say, oh, tell me something about it, well, you know the eigenvalues now of that matrix just by looking at the diagonal entries. That's proposition 518. Proposition 520. Now these may be somewhat restrictive, but suppose that you have dimension V distinct eigenvalues. What do you know now about the matrix representation of the map? Now you can create a diagonal matrix representation. Granted, you have distinct eigenvalues and you have dimension V of those, Nevada of those. If you had a 10th order system, and I probably won't give you anything more than a 12th order system, because we might be playing Monopoly Wednesday, right? I might give you a Markov chain that has 12 states to it, right? Seriously. I don't know. Probably not. But I could, and you should be able to sort of build something up. Maybe I won't ask you to find the eigenvalues and eigenvectors unless there's special structure. If I gave you a 12th order diagonal matrix, you have quite a bit of information. Now, if you just had a generic matrix that's 12 by 12, that might be a little bit challenging to find the eigenvalues and eigenvectors for. But if it's upper triangular or diagonal, that makes it pretty easy. If it's diagonal, now you basically have a bunch of one-dimensional problems. It's decoupled. Everything is sort of just one, playing with itself. That's the beauty of having these diagonal matrices. The additional benefit, well, not additional, but the upper triangulars, at least they're just playing sort of with subsequent neighbors. Or preceding, I should say, preceding neighbors, if it's upper triangular. They're playing with more than just themselves, possibly. Diagonal, it's just themselves. Then we have proposition 521 that gives us a lot of different relationships or following statements that are equivalent with respect to diagonal matrix, eigenvectors of T being representing the basis of V. You have all of these one-dimensional subspaces, U1, U2, that form a direct sum decomposition of your overall vector space V. You can look at the null space of T minus lambda I, and that gives you a vector. You can put that in together with the null space of T minus lambda sub 2I, etc., and that builds up your entire system, and the dimension of all of that is equal to the dimension of V. That's proposition 521. A lot there. Now, some other propositions at the very end of chapter 5 deal with real vector spaces. And we actually talked about that just a little bit ago. If we were dealing with real vector spaces, now we may not have an eigenvalue for a 2 by 2 matrix or a 2 by 2 submatrix. But we may have then invariant subspaces that are 1 or 2-dimensional. And that's what Theorem 524 says when we're dealing with real vector spaces. We have invariant subspaces of dimension 1 or 2. And that goes back to this guy. We may have a 2-dimensional subspace. We may not have an eigenvalue for that matrix, but we do have a 2-dimensional subspace associated with that real vector space. (526) says if you have an odd dimensional real vector space, then you do have an eigenvalue. Why is that? Because if you now have something odd, you have to have a real root. And once you have a real root, then you have an eigenvalue. We didn't cover that in class? Who knows what we're going to cover on the exam and what we covered in class. So the question was, we didn't cover that in class. Well, we covered it now. It's now in class. Okay, so we may have stopped earlier, but all of this other stuff we kind of need to know. Because it's good stuff. So now if you have an odd dimensional real vector space, now you have a real eigenvalue hanging out there. And that says, oh, now I do have an eigenvalue. All right, so if you're tired of chapter 5, we can move into chapter 6. Chapter 6, probably aren't any more results in chapter 5. So chapter 6 is dealing with inner product spaces, which up to that point, we really haven't had to worry, or we didn't worry about length of vectors. We didn't worry about angles between vectors. We didn't worry about vectors being orthogonal. Now we can, once we've built up or defined these ideas of an inner product and attached that to our vector spaces. Now we can have not a CVS, but a CIPS, right? Complex inner product space, a real inner product space. And that provides us with more material to test you on. Actually, more material to know, which is good material. But you need to know, for example, when we're dealing with inner products, that really says that we have certain properties, doesn't it, of inner products? Those being positivity, definiteness, additivity in the first slot, homogeneity in the first slot, and conjugate symmetry. And you should be comfortable with those, playing with those and using those properties. Or if I give you a potential inner product and say, is this an inner product? Oh, seems to satisfy all the properties. But we also have other ways of checking that, don't we? Maybe the parallelogram equality. If that is violated, because in one of the homeworks, you weren't even told what the inner product was. You were just given sort of norm conditions, and saying, is the inner product that these norms come from, is it valid? And there you said, I don't know, I can't check any of these properties. But you can use some relationships on norms that deal with inner products. And I think you even, in one of the homeworks, didn't you have like the norm of u plus v minus or plus the norm of u minus v divided by 4 is equal to the inner product? So that has to be true for an inner product. And that's dealing with norms, isn't it? That was on a real inner product, I believe, that one. The other one had some eyes floating around in it. All right, where were we? Well, now we can start talking about the Pythagorean theorem. A squared plus b squared is equal to c squared. But the nice thing about that, or the reason that is true, is because a and b are orthogonal, aren't they? So we can call a timeout and we can say 6.3, Pythagorean theorem. All right? And the other thing that we have orthogonality with is now we can rewrite any vector u as being along a direction, some vector, and then its orthogonal component. So we could now say that we could look at uv over v squared in the direction of v, what component of u is in the direction of v, and then add to that the component that's orthogonal to that, which is u minus that same piece, uv, whoops, that's supposed to be a v, and that's a nice thing to be able to do, is to break down a vector into a direction that you want to proceed and then move orthogonal to that. And that relationship is nice. Now you have alpha v plus a w, where w is orthogonal to v. And you pick that alpha properly, that weighting that you move in the direction along v. Having that now allows us to introduce more concepts. One is the Cauchy-Schwarz inequality. Which tells us something about the norm of the inner product. So if that was v and u, we know that that's now less than or equal to the product of the norms of v and u. The triangle inequality is really just a generalization of the idea of a triangle. Two sides, the sum of those two sides have to be bigger than the third side's length, is really what the triangle inequality is saying. So that we now have u plus v is less than or equal to the norm of u plus the norm of v. And being able to use that. So if you need to bound something, you can now bound this u plus v. If you had direct vectors, now you have an upper bound for that by means of the triangle inequality. We talked about this just a minute ago as a way to potentially invalidate or find a counterexample for whether or not something is a valid inner product. And that was the parallelogram equality, which says what? I like to sort of just draw a distorted envelope, meaning if you now have a parallelogram, if you looked at these diagonals, which are not necessarily the same length, if this is a distorted rectangle, what do we know about those red lines? The sum of the squares of their length, or the sum of the squares of the norms, is equal to the squared norms of all the perimeter. That's the parallelogram equality. And so you could just draw that picture and boom, you have it, if you didn't include it on your sheet. But now you can use that to your advantage to maybe solve for the length of one of those sides. That was a homework problem, I believe. You were maybe given something about u plus v's norm and u minus v's norm. And that's just those red lines. Now that we have those ideas of orthogonality and we have an inner product, now we can start creating basis vectors that are actually orthonormal. And if we do, then this, I think, we were sort of using today when we were talking about the norm of TE1, or the norm squared. Proposition 615 says if you have some vector that's expressed in terms of an orthonormal set of bases, so if you're dealing with E1 through E sub n being a set of basis vectors that are orthonormal, then if you had a V that was maybe an A11 E1, or maybe I don't want to put so many subscripts on it, let me just call this A1. A1 is scaling E1, and A2 is scaling E2. And maybe that's your V. Now if somebody says, well, what's the square of the length of V? What's the square of the norm of V? If E's are orthonormal, that's pretty easy, isn't it? Now you just take the weighting or the scaling, take its absolute value and square it and add them up. Now that's equal to A1 squared absolute value, the absolute value of A sub 2 squared, etc. We even have corollaries that are important in chapter 6. Corollary 616 says if you have an orthonormal list, can you say anything about that? I just give you two vectors, and maybe they're 10 tall. What do you know if that list that's TWO long, that's of length 2, do you know anything about that if I said this list is an orthonormal list? Can you say anything more about that set or list of vectors? Pardon? Okay, their inner products will be 0, won't they? So what does that maybe tell you? Now they're not only orthogonal, but they're linearly independent, aren't they? So if we now have a list of orthonormal vectors, they're going to be linearly independent. And that's what corollary 616 says. So you're playing on the fact that they're orthogonal because that means that they're not lined up, are they? You could have vectors that are linearly independent, but now the orthonormal list says you're going here, and then you're going here, and then you're going straight up with these vectors that are spanning or creating your orthonormal list. So this orthonormal list, whatever length it is, forms a linearly independent list of vectors. And you can use those orthonormal basis vectors to build up a representation of any vector in your vector space. If you had a vector v, what do? Well, you find the component of v lying along each of those orthonormal directions. And you can do that by an inner product. And since they're orthonormal, you don't have to worry about dividing by anything. It's already properly scaled. Now you just take v, an inner product with the first orthonormal vector, and that will weight that direction E1. Then you take v with the second direction inner product. And you can just do that for all the directions. Some of those may be 0, which just means that v didn't have a component in that direction of the basis. But this is now a way to build up a representation on an orthonormal basis of v. And that's Theorem 617. And you now know, if you use one of the earlier results, which is just hiding above, Prop 615, you now know how to find the norm of v if somebody gave you this parameterized form of that vector v. You can just take all of those inner products, take the absolute value and square them and add them up, and now you have the square of the norm of v. All of these notions of being orthogonal and orthonormal get applied when we start looking at building things up nicely with the Gram-Schmidt orthogonalization approach, which is the Gram-Schmidt, I don't know, what did we call it, a theorem? I think the book just says 620 Gram-Schmidt. But now you can build things up using the Gram-Schmidt approach. And if I just give you a list of linearly independent vectors, you can now build up, because now we're seeing how powerful these orthonormal vectors are. The Gram-Schmidt procedure allows you to build or create an orthonormal list just based on a collection or a list of linearly independent vectors. And that's an important thing, and you need to be able to do it, and I think you did it on the homework several, or maybe a couple of times. One with a vector space that was a polynomial, right? Second order polynomial. You were using a particular inner product. You also maybe needed to do it for more conventional vectors, in R4, for example. That's Gram-Schmidt. Corollary 624 is sort of an interesting corollary. That says every finite dimensional inner product space has an orthonormal basis. So every finite dimensional inner product space has an orthonormal basis. Six 625 says if I give you 3 vectors in a 6-dimensional space, and I tell you to give me an orthonormal basis for the 6-dimensional space, is that even doable? So I say, okay, you're working in R6. and I give you 3 linearly independent vectors in R6, and then I say, give me an orthonormal basis for R6. Can you do that? You need to find 3 more vectors that are linearly independent of the 3 that I gave you, and then just start building it up with the Gram-Schmidt procedure and find these orthonormal bases. So you can extend a list of vectors to create a basis for subspaces or for the entire vector space. Corollary 625. Corollary 627 starts talking about T having, and so in 627, if you have a linear operator on V, then you can find an upper triangular representation in some basis for that linear operator T. That's 627. Then we can start talking, and I'm skipping a few. So now we start talking about orthogonal complements, moving in orthogonal directions, or using subspace behavior like you could think in terms of two-dimensional. You go in along one vector, and then you go orthogonal. Now we're dealing with subspaces, and now you maybe want to break things up into living in that subspace and then going orthogonal to that subspace. And that now provides us with this, whoops, I'm getting ahead of myself. I jumped down before I wanted to jump down. First is the orthogonal complement. Concept. And that is Theorem 629. If U is a subspace of V, then you can actually write you can write V, the whole subspace, as a direct sum decomposition of U with its orthogonal complement subspace. And U perp is always a subspace. We've shown that. Even if U is just a subset, U perp is a subspace. And we also know that if we take the orthogonal complement of an orthogonal complement, we're back to where we began. Now that we've separated things out into orthogonal complements, now we can start projecting along that orthogonal complement so that we now have orthogonal projection. And if we start with E1, E2, EM being an orthonormal basis of a subspace, let's say of U, then we can find the orthogonal projection into U of any vector V by simply taking V inner product with E1 in the direction of E1, etc., V E sub M inner product with E sub M for every vector V. And that's going to give us now a result that allows us to deal with sort of the closest vector in a subspace U to maybe some vector V that doesn't live in U. If V lived in U, then we could just create V out of those orthonormal basis vectors in U. But if we don't, then we can find the smallest by going orthogonal to that subspace U. So that's that sort of norm of V minus P sub U of V being less than or equal to the norm of V minus U for all U. Where this is now, if you compute that vector, that's the sweet spot. That's now as close as you can get in the subspace U. Then we ended up with two more things in chapter 6. We had linear functionals, and adjoints. Linear functionals, you actually, I think, had a problem with that on homework 7. If you now have a linear functional, then you can actually find this unique vector V based on that linear functional that allows you to simply compute an inner product in order to find, let's say, phi of U. You can now do the inner product of V with U, where V was that unique vector that you wanted to find. So that is, I think, Theorem 645. Which says that V is now, let's say, some phi of E1. Maybe if it's in a complex vector space, you need to take the complex conjugate of that times E1 plus phi of E2, etc., down to e to the n. And then that allows you to compute this inner product of U and V, which will be the same as phi of U. And that's a pretty powerful result. Now you can build up this vector and now just start computing inner products, which might be easier than this linear functional applied to some vector U. Then we have adjoints. What's the definition of an adjoint? That's all based on inner products, which is why we're seeing it in chapter 6. Now if we had TVW, what's that equal to, or how does that define the adjoint? And now we can use that result to find the adjoint of T. And you should be able to build these up. If I give you a linear map, can you find the adjoint of that linear map? And it's based on, let's say, this defining relationship. The other thing that you probably want to, there's a couple more things with the adjoint. Proposition 646, skipped one, didn't I? 646 tells you how the map and its adjoint, these different spaces, are related. The null space of T, what that looks like relative to the adjoint subspace, etc. And if I give you some in the homework problem, I think you were sort of all or nothing. It was surjective or injective. So if it's injective, what do you know about the null space? For an injective map, the null space is trivial, isn't it? If you have a surjective map, then it's covering that entire codomain. So you sort of were doing all or nothing. But now I could give you maybe some non-trivial null spaces, or maybe something that's not surjective. But you could still relate that to either the linear map or its adjoint based on proposition 646. That told you a relationship. For example, I think the first part said something about the null space of the adjoint map being equal to the range space of the orthogonal complement to the range space of T. It's sort of it's a dual nature thing, null space and range space, and now you have these different maps. And you can do the same thing for B, C, D, and E. Meaning if I now gave you that the null space of the adjoint contained a certain vector, could you tell me something about the range space of T? In the homework, it was all sort of all or nothing. You were sort of saying, oh, the null space of the adjoint of T is trivial. Then you know the range space of T is covering everything, since the perp of that was trivial. But if you don't have those conditions, now what do you have? Now you have to be playing with, if I said, okay, the null space of the adjoint of T is the x-axis in a three-dimensional space. So now if you operated on anything in the x-axis with the adjoint map, that would map to the 0 vector. What's that tell you about the linear map T? Well, now you know the x-axis is in the orthogonal complement to the range space of T. So the range space of T in a three-dimensional space must be covering YZ, the YZ plane. Those are the kinds of ideas or concepts that can be obtained from this proposition. It doesn't have to be all or nothing like the homework. Finally, we have proposition 647, which says that if we have orthonormal basis, if we have orthonormal basis, then we can say something about the linear map and its adjoint. They're related by the complex conjugate transpose, or the conjugate transpose. So if I gave you this, the matrix representation of T, and you have a trivial orthonormal basis would be the standard basis, wouldn't it? So if everything's in the standard basis, we can apply proposition 647. Now if I wanted to find if this was now A, what would the matrix representation of the adjoint map be? It would be the conjugate transpose of A, wouldn't it? That's proposition 647. So, study these theorems, corollaries, propositions, and probably take down some examples that fit those propositions, theorems, and get that concept in your head, like we just did with proposition 4P 646, where we were talking about the null space relationship with the perp of the range space of T. Oh, if I just had that in the x-axis, what does that mean about the range space of T? Have some physical examples for these different theorems and propositions and feel comfortable manipulating those, because that's maybe what you'll be tested on. Just stating these, but knowing kind of how to prove those results also, because that will be helpful in some of these questions. Do have office hours tomorrow and Wednesday. I couldn't even remember what today was. and send me email if you have questions. Good luck. Don't forget your homework. Homework 7 is due today.